Welcome to Notes 2.2b, finding polynomial functions of a higher degree. So the first question says, find a polynomial with zeros x of negative 1/2, 3, and 3. So the way I could write this out is I can say x plus 1/2, x minus 3, and x minus 3. Those are my zeros. Whenever I plug that fraction in, I can do that bottoms up here so that it actually can become a polynomial. And so now it just wants me to distribute and solve to actually find a polynomial that equals this. One thing to keep in mind is that if you have two of the same zero, like a repeated zero, you still would plug it in twice because it's a zero that has a multiplicity of 2. There's 2 of them, but we still plug it in. So I'm going to go ahead and FOIL this guy here. So I get x squared minus 6x plus 9. And then now I'm going to distribute these guys while I drop my pen. So I get 2x cubed minus 12x squared plus 9. And then I'm going to distribute this way too. Plus x squared minus 6x plus 9. Oh, sorry, this one should have been a 9x, right? 2x times 9. This actually should have been an 18x. I'm not sure what I was thinking there. So it should have been 2x cubed minus 12x squared plus 18x plus x squared minus 6x plus 9. So this is where we should be. And now we can just combine like terms. So we would have 2x cubed minus 11x squared plus 12x plus 9. And this would be our polynomial. Now, why does it say there's many correct solutions? I could have added in extra zeros. It just has to have at least these zeros. I could have added an x plus 5 to the end. I could have added a negative out front. I could have done a lot of things to this function and it will still give me these zeros. This is the most simple one that we can do. So I'm just going to stop there, but you could have done something different as well to get there. So the next one says, sketch the graph of 3x to the fourth minus 4x cubed by hand. What? Well, let's think about this. We have a leading coefficient test that tells us that we have a positive leading coefficient and an even exponent. So we know this one is going to rise to the left and right. So we know that much about our graph. What else can we know? Can we solve for our zeros at all? Absolutely. So we have 3x to the fourth minus 4x cubed. Can we factor this? Sure. We have 3 x's that we can pull out here. So we know x is going to be 0 with a multiplicity of 3. And x is going to equal 4/3 with a multiplicity of 1 there. So we're going to have x-intercepts at 0, 0, and 4/3. And these points will be on our graph. So now we could just plot a few additional points. Let's figure out, like with an XY chart. Let's say we'll plug in 0.5, 1, 1.5, and yeah, we'll do 0 too. So if we plug in 0, we get 0. If we plug in 0.5, let's see what we get. I can actually just type this into my table. 3x to the fourth minus 4x, cubed. Get my graph. I didn't have to actually hit graph. I have a really bad habit of hitting that graph button before. If I'm trying to hit table, I don't hit the second button, and then I have to sit and wait for it to load. So here we are. Okay, so now I can change this. Let's see, 0 gives me 0. What about 0.5? Go to. 0.5 gives me negative 0.3125. What about when I plug in 1? What do I get? Negative 1. And we could have plugged each of these in by hand. I thought it might have been faster if we did that with how slow I was being with my calculator. But most times it should be faster this way. So we get these points. And so now we can actually draw our graph. So we know we're going to have 0, 0 and 4/3 0, right? So a little bit past 1. These are our 2 zeros that we came from here. We know that it's going to rise to the left and to the right. And then we also know that because this has a multiplicity of 3, that we're going to go through the origin, and we're going to go through the origin on this because both of these have odd multiplicities. And so now I can just plot my additional points that were put in between these. So like at 1.5, I'm at 1.67, so somewhere like up there. At 1, I should be at -1. At 0.5, I should be at -0.321. So you kind of get something like this, which looks about right for a power of 4, right? 1, 2, 3, 4. We got our little loops going on. Awesome. Okay, next. Sketching the graph of the polynomial function. So this is another similar problem. So let's look first at the leading coefficient test. What do we have? We have a negative coefficient and an odd degree. So we know it's going to rise left and fall right. So now we need to find the real zeros of the polynomial by factoring. So all of these have an x that we can pull out, and we could actually divide by 1/2 to all of these and get that negative out of there too. So we're going to pull out a -1/2 x. If we do that, half of 2, if we divide that by half, we actually get 4, because we pulled out a 1/2, so we're actually doubling this. We're doubling it to get rid of that 9/2. And then we would have minus, because we pulled out the negative. We're going to double this, 12x. We pulled out an x. And then this becomes positive because we pulled out the negative, 9. And we pulled out the x. So that gets rid of that denominator there. So if I solve for here, we know that x could equal 0. That has a multiplicity of 1. And then here, I am going to need to look at this one. We actually could do it by grouping, because we can pull out a 4x here. So both of those have 4x. So we get 4x, and then we have x minus 3 there left, plus 9. Did that help us at all? Not particularly. So let's see what else we could do. We actually see that we have perfect squares on the outside here. So we have a 4x squared, which 2x, and 3. So I wonder what would happen if we tried 2x minus 3 for that perfect squared. 4x squared minus 6x gives us -12. Then -3 gives us 9. So this one was one of those perfect square situations. And so in this case, we would have 3/2, but we would have a multiplicity of 2, which is going to tell us a little bit different thing there. So for number 3, let's go ahead and plot some additional points. So we're going to make an XY chart. I'm going to plot some points on either side of these zeros. So -0.5, we'll try 0.5 because that's in the middle there. 1, another point in the middle, and then 2. I can just plug the equation into my graph, and hopefully I'll do it a little bit faster this time. -1/2 x times 4x squared minus 12x plus 9. Go to our table. -0.5, 0.5, 1, and 2. So I get 4, 1, or 4, -1. I can't see it. 4, -1, -0.5, and -1. So now, when I actually go to draw my graph, I can see that I'm going to have a point at 0, 0, and at 3/2, because those are my zeros. I know that I'm going to be going up to the left, and I know I'm going to be going down to the right because of my test. This one has a multiplicity of 1, so it's going to go straight through. This one's going to have a multiplicity of 2, so it's going to come up and touch. So let's plot our additional points. -0.5 is at 4, which totally makes sense because this should be rising. 0.5 should be at -1, which makes sense because that's going through. At 1, we should be at -0.5. So coming back up a little bit towards this. We know this is going to just turn right back around because it has a multiplicity of 2. And at 2, we are at -1, which makes sense because we continue to fall there. Perfect. Okay, intermediate value theorem. Sounds crazy. It's really not. It just states that if we have some points here, an x and a y, that are in the same function, and they don't equal each other, for any number, there must be a number between them such that it crosses through. So if we have a point down here at 1 and a point down here at 3, there's going to be somewhere that it crosses through to, just because it's in the middle of it. That's all that it's saying. If we have 2 points that are in the same function and they're not the same thing, if whatever's in between them, that function will cross it at some point, as long as it's actually a function. Okay, find 3 intervals of length in which the polynomial is guaranteed to have a 0. So we could actually do a graphical solution for this. We could just plug it in. Let's look at it. So we have 12x cubed minus 32x squared plus 3x plus 5. Let's graph this guy out. Here he goes. And so from our figure, we could see that it crosses our x-axis 3 times. We could actually calculate our 0. Oops, I didn't mean to calculate value. We want to calculate the 0. We go to the left of it and the right of it. We have a 0 at negative 1/3 here. Let me make sure I typed it in right. 12x cubed minus 32x plus 3x plus 5. Yep. And we can find another 0 here to here at 5. And so we could say that, like, we know that there's going to be a 0 between 0 and, let's see where the next one is really quick. So at negative 1/3, 5, and where else? Oh, was that 0.5? 2.5. That first one should have been 0.5. That makes more sense. I was a little confused there. I was like, did I type that in right? And so basically, we know that we could have a 0 anywhere between these two values, say between 0 and 2. I know that there's going to be a 0 by the intermediate value theorem because we have a 0, like we're crossing through it from 0 to 2. We know that we're going to cross the x-axis, so there must be a 0 between it. We could also do a numerical solution of this by looking at the table. If we had negative 2, negative 1, 0, 1, 2. So like here, we know from negative 1 to 0, we're going to cross the x-axis because it's going from negative 42 to 5. So by the intermediate value theorem, we can say we know between negative 1 and 0, there has to be a point where this function crosses the x-axis. Just so happens that it's at negative 1/3. But we can kind of estimate our graphs that way by just knowing that if it's crossing through, it's going to be somewhere in the middle.